let's consider the situation in the image. We have two solenoids, the one on the left that we are calling primary coil, and the one on the right that we call the secondary coil. The primary coil is connected to what we call an AC generator. That is a generator of electricity that alternates in time, meaning that the current is going to flow in one direction for half a period and the opposite direction for the other half of the period. That's the way we get our power supply at home. Now, the secondary coil is not connected to any generator. It is instead connected to a meter that's capable of measuring for us induced currents, if there is any. Now, notice that the coils are a proximity of each other, meaning that if the first coil is going to produce a magnetic field, the second coil is going to be subject to that magnetic field, and vice versa. So let's focus a little bit on what's happening here. Because we have a generator that's feeding the primary coil through a change in current, the primary coil is going to produce a magnetic field that's going to be changing as well. Remember, the magnetic field due to a solenoid is given by mu n I. I is obviously the current in the primary, and n the number of loops per unit length in the solenoid of the primary. Now we are using the simple case of just a solenoid where we have that expression. Now, in all cases, even if the equation is going to change a little bit, if we have a different type of coil, it's still going to be proportional to I. That magnetic field that's produced by the primary and that is changing, it's going to affect the secondary coil. The secondary coil is going to experience the field that is changing. Regardless of changing or not changing, if I have a coil that's subject to a magnetic field, that means it's going to be subject to a magnetic flux. And a magnetic flux is given by B times A. Magnetic field times area. Area would be the cross-sectional area here. B is the magnetic field that's due to the primary coil. So in other words, this B here, when we write the magnetic field, this B is B from the primary, and A is the area of the secondary. Now, if we call phi s the flux through one loop, if I have n loops, I'm going to have a total flux of n sub s times phi sub s. Now, if we pay attention to this equation, it is B times A sub s, and B is mu times n times I sub p. So if I take the expression for B and replace it here, what I get is phi sub s is equal to mu n I sub p A. You notice here that phi sub s is proportional to I sub p. That's what we have written here. Now, the proportionality constant M we define as mutual inductance. We call it mutual because it's between two coils. And the word mutual is used because if we reverse the role and have the AC generator here and the meter here, we are going to have the same behavior, and essentially we are going to encounter back that same value of n. That's why we call it mutual. Now that we have this proportionality established, let's focus back on the fact that that change in flux is actually, that flux is actually changing. From what we know from the past, if we have a change in flux, then we are going to have an induced EMF, which is given by this expression. Now, if we use this relationship for the flux, this expression is going to give me minus MIP final minus MIP initial over delta t, which leads us to this expression, which gives us the EMF in a secondary coil is given by the mutual inductance times the change in the current in the primary per unit time, with a minus sign, of course, accounting for Lenz's law.